All right, so this is chapter 10, section 5. Apply other angle relationships in circles. So the first theorem, theorem 1011, is super duper close to, actually, it's the same exact equation, but it's very similar to inscribed angle theorem. Like I said, to the point where the equation is the same. So we have a circle, we have a chord, BA, and we have a line tangent to that chord. Whoops, that's not tangent. We have a line tangent, so touching the circle at exactly one spot. Okay. We have this arc here. We have this arc over here. And we can almost consider this like a inscribed circle, right? It's a inscribed circle is a angle where the point is on the circle. So here's the point on the circle. If we expand this guy out this way, this would be the captured arc. We can call this angle number 2. And if we expand this guy this way on the other side, this is the captured arc here to the right, and we can call that angle number 1. And what theorem 1011 says is that if I'm looking at angle 1, it's going to be half the measure of its intercepted arc. So here's the arc. It's being captured or intercepted. It's going to be half of that. So half the measure of AB. And if I wanted to find out what angle 2 was, it would be half the measure of that arc, and that's arc BCA. And that'd be half that measure. Okay. So the theorem says if a tangent and a chord intersects at a point of the circle, here's a chord, here's a tangent, they intersect on a circle, then the measure of each angle formed is 1/2 the measure of its intersected arc. Okay, so we have 3 examples of that. If we take a look at number 1, we have a circle, and we have a tangent line like so. Close enough. Here's my chord. Here's angle 1. Here is the intercepted arc of angle 1, right? If I was to expand this guy this way, this is captured and it's 210 degrees. We want to know how much angle 1 is. So if we use theorem 1011, we have that angle 1 is equal to half of that arc, which is half of 210. So we can say that angle 1 is equal to 105 degrees. All right, when we have number 2, when we have a circle, we have a chord right here. Here's our tangent line. And this guy is 98 degrees. We have a point here at T, here at S, here at R. And we want to know what the measure of TSR is. What is that? RST. So what is this guy? And we will use our handy dandy theorem 1011 equation, and we can say that angle 38, or 98 rather, is equal to half the measure of RST. So I'm multiplying both sides by 2. So 98 equals 196 degrees. Or RST rather, equals 196 degrees. Then we have number 3. And what number 3 says, we have a circle over here. Here's our tangent right there. Here's our chord. Here's y. Here's x. And this guy is 80 degrees. They want to know what the measure of arc XY is. So how much is this guy right here? Okay, using the same equation, 80 degrees is equal to 1/2 the measure of XY. Multiply both sides by 2, the measure of XY is equal to 160 degrees. So that equation was an equation where the chord and of the angle, one of the sides of the angle was a chord, and the other side of the angle is a tangent line. So what does that look like when we have our intersection inside? So we've dealt with various intersection points to this point in this chapter. So the first one was what happens if the intersection is in the circle, like so, right? What does that angle look like? What happens when the intersection is on the inscribed arc? So that's that scenario. What happens when the intersection is a chord and a tangent line? How does that work, right? We just did that. Now we're going to do a situation similar to number 1, but we have an intersection of chords where it's not going through the center. Here, we can say that's the center, right, of the circle. Right there. Here, this is not the center circle. And that's going to be our next step. There are other avenues as well, intersections that we'll talk about outside of the circle. And that would be our 5th scenario, and that's coming up post haste. So what happens if we have a circle and we have 2 lines and they intersect outside the circle? What does that look like? So those are all the scenarios that we've looked at so far. We've talked about 1, 2, and we just did 3, and now we're going to finish it off by talking about the 4th, then the 5th scenario. So what happens when we intersect and it goes inside? And this is theorem 1012. Angles inside of a circle theorem. I'm not going to write all of that. I'm just going to call it 1012. So here's our circle. Here's our angle, and we have 2 chords such that they intersect inside. We'll call this guy AB. We'll call this guy DC over here. All right, we have angle 2 and we have angle 1. That's angle 2 and angle 1. Okay. So if we look at angle 1, actually let's do it like this. Angle 2 and angle 1. All right, so if we look at angle 1, if we look at angle 1 and we look at its captured arc, it's going to be DC. All right. We also know that this is a vertical angle, right? So this guy right here can also be considered 1, and it also has a captured arc over here, like so. So that captured arc and that captured arc, we have 2. We have arc DC, we have arc BC. So what theorem 1012 says is that if I want to find angle 1, I'm going to add these 2 arcs. So that's going to be equal half the measure of arc DC, the sum of arc DC, and arc AB. Okay. We're going to add these 2 guys together and divide it by 2. If I'm looking at angle 2, angle 2 goes this way. Angle 2 goes that way. So I have this arc right here, which is arc BC. It also goes this way, and it goes this way. And I have this arc over here as well, and that's arc AD. So if I have to look for the measure of angle 2, that's going to be half the sum of arc BC, arc AD, plus arc BC. Okay? Half the measure of arc AD plus arc BC. And that's going to give us our angle for number 2. Again, this occurs when the intersection happens inside of the circle, not at the center of the circle. Okay? That's 1012. Then we have 1013. 1013 has 3 scenarios, but we have 1 equation. How neat is that? So I'll do all the scenarios since it's given here. Angles outside of a circle theorem. So if we have case scenario number 1, we have circle here. We have the intersection out here. So we have this ray and this ray going that way. We have intersection at, oh, that's A. At A, we have an intersection at B, and then, oh, I gotta start over. That's a tangent line. We have a tangent line. That's what I get for not looking at the picture correctly. All right, so we have an intersection at A. We have an intersection at B. And then we have our tangent line at C. We're going to call this here angle 1. This is going to be my inside arc that's captured. And this is going to be my outside arc that's captured or intercepted. Okay. So notice that the outside arc is always going to be bigger. I'll use a different color. The outside arc is always going to be bigger than the inside arc when the intersection occurs outside of the circle. So we have arc BC, we have arc AC. So if I wanted to find angle 1, that's going to be half the difference of the arcs. So half the measure of BC, and it has to be BC first, has to be the outside arc, minus the measure of AC, the inside arc. All right, this should not be a negative number. This should always be a positive number. So we always have the outside minus the inside arc, okay? So that's case scenario number 1. We have a chord that goes through 2 points on the circle, and we have a tangent line. All right. Case scenario number 2, and by the way, all the equations are going to be exactly the same. You're going to be half of the difference of the outside minus the inside. But these are the 3 different cases where you can use it. Okay. Case scenario number 2. We have a circle, but instead of having a chord and a tangent line, we have 2 tangent lines. So we have a tangent line here and a tangent line here. All right, they call this P, they call this R, and they call this Q. All right. Here's my angle 1 right here. Here's my inside arc. Here's my outside arc. Okay, the outside arc is PQR, the inside arc is PR. When it has tangent lines, and actually, I might be able to draw. Actually, I'll get to it. I'll come back to this in a second because I think I can draw this side over here. Equation is exactly the same. So let's call this angle 2 now. This is angle 2. We can say that the measure of angle 2 is equal to 1/2 the measure of the outside arc, which is PQR, minus the inside arc, which is PR. Okay? Outside minus the inside arc. Okay. So that's case number 2. And then case number 3. We're going to have 2 chords going through both circles, so no tangent lines. One outside goes this way, outside goes that way. We have a W, we have an X, we have a Y, we have a Z. We'll call this guy angle 3, and my inside arc here is WZ, and my outside arc is XY. Again, same equation. We're subtracting the outside arc, which is always the bigger arc, minus the inside arc. And when I say outside and inside, I mean outside and inside in relation to the angle. So the closest arc to the angle is my inside angle. The closest arc, or the next arc further away from the angle, is my outside angle. So if I wanted to find the measure of angle 2, that is going to equal half. Actually, that's right there. Measure of angle 2 is going to equal half the difference of the measure WX. Oops, I'm sorry. XY minus the measure of WX. WZ. Because I can't read sometimes. Okay. Alright, the outside minus the inside. Okay. 3 scenarios, same equation. Angle is the difference of the outside arc minus the inside arc divided by 2. Case 1, one chord that goes through both circles and a tangent. Case 2, both rays are tangent to the circle, and in case 3, both rays or lines are intersecting the circle at 2 points. That's what I was talking about in terms of case number 2. Since I have 2 tangent lines here, Um, the whole entire circle is captured at one point in time, either by the inside arc or the outside arc. Uh, they're both fully captured. The whole circle is captured. If you look at case number one, it's only partially captured. Right? This part here, AB, is not captured. If I look at case number three, WZ is captured, XY is captured, but WX not captured or intercepted, and then ZY not captured or intercepted. But when it comes to tangent, the whole circle is intercepted. So if I wanted to find out what these guys were in terms of what they sum up to, if I was to actually add these guys, so if I was to add PR, the measure of PR, plus the measure of PQR, I know that since the whole circle is captured, if I add them up, I'm going to get 360 degrees. Right? So when you have the case number two, tangent lines intersecting outside, if I add the two arcs, the inside and outside, I'm going to get 360 degrees. And that's going to come in handy when we start doing one of the problems. Okay. So if you look at number one, or four rather, we have a circle, we have some intersection inside of the circle. I'm going to call this guy over here Y. This arc over here is 95. Inside here is 102. And then we have point A, point B, point C, point D. Okay? A, B, C, and D. We want to know what Y is. Since the intersection is occurring inside of the arc, we want these two guys right here. I know that this is 102. So if I use a linear pairs, I can subtract 180 minus 102 to get that guy, and that guy right here is 78. So I want this angle associated with this arc and that arc. So we have enough to solve this. We can say that using theorem 10, I believe, measure, well, I'll say 78. 78 is equal to half of the measure of DC and AD. So 78 is equal to 1/2 95 plus y. Multiply both sides by 2, and I get that 156 is equal to 95 plus y, subtract by 95. And we get that arc on the other side is equal to 61 degrees. Voila. Or you can say the measure of arc AB is equal to 61. Okay, so that's number 4. Number 5. We have a circle. We have a guy going this way. Going that way. This is K, J, H, G, and alpha. We're told that this is 30 degrees. So, and we're also told that this guy over here is 44 degrees. They want us to find FG, and they call it A. Okay, so using 1011, no, 1013, one of the three. We have the measure of angle J is equal to 1/2 the difference of the outside minus the inside. So half the measure of angle FG minus the measure of KH. So J is 30. FG is what we're looking for. And then this is 44. Multiply both sides by 2, we get 60 is equal to 1/2. Oops, 60 is equal to A minus 44. Add 44 to both sides, and we get that A is equal to 104 degrees. Or we can say the measure of angle FG, or arc FG, is equal to 104 degrees. Okay. All right, so number 6. I think it would be a good idea to do it twice. So they actually have an example of it, which is exactly what number 6 is. So let's do that. So we have the Earth. Is there Earth? And there's the Aurora Borealis going on, the Northern Lights. And it flashes at some point C. So here's our intersection point. And these lines are going to be tangent over here and tangent over here. All right. We have the center of this circle, center of our Earth. We have that point A. We have point D. We have point B. We have point C. This guy is 150 miles above the Earth. This is not to scale. So the distance between here and here, so the radius of the Earth plus 150 degrees, that's going to be 4,150 miles. And then we have the radius right here, 2 point D. We have the radius right here, 2 point D. So remember, from the radius, and the radius is 4,000. The radius to the tangent line is always 90 degrees. So this is a 90 degree, this is a 90 degree. This is a perpendicular bisector. So that means that this angle and this angle here, these guys are congruent angles. So we need to find out, or the book wants us to find out, what is the measure of the arc closest to the Northern Lights. So what is the measure of the inside arc? Okay. We have enough information to solve this, so we need to do a couple of things first. Thing number 1 is we got to define these arcs. So we have an inside arc, we have the outside arc. Remember that these are tangent lines, and we had discussed earlier, and the reason why we discussed it earlier, because I knew we were going to do this problem, is that if we have two tangent lines at an intersection outside of the circle, then the inside arc and the outside arc adds up to 360 degrees. So if this is X, let's call this guy for right now Y. I know that. Let's call this number 1. Let's establish what these guys are first. X plus Y equals 360 degrees. All right. So if I wanted to know what Y is, I'm going to subtract X from both sides, and I can say that Y is equal to 360 minus X. So instead of calling this guy y, I want to call this guy 360 minus x. Okay? So we have our two arcs defined. We have x, and you have 360 minus x. Hallelujah. Let's take a look-see at, so that's step number one. Step number two, let's take a look-see. I don't know how that's going to fit. Actually, let's put 2 down here. At this triangle right here. It is a right triangle. And I have 2 of the sides defined. I have the hypotenuse, right, because it's opposite of the 90-degree angle, which is 4150, and I have this leg right here, which is the radius of the Earth, which is 4,000. And I want to find this angle for right now. Well, I can use trigonometry, and I can say that from this angle's perspective, it's opposite over hypotenuse. So I can inverse sine opposite over hypotenuse. And that's going to give me angle ACB. And that is going to be 74.5, let's say 5.5. Let's say 548. All right. However, that's not the whole angle that I want. That's only half of the angle. I want this whole entire angle here. I want angle BCD. So since I have half the angle, because I know it's a perpendicular bisector, I can multiply this by 2. So step 3, multiply 2 times 74.548. And that gives me angle BCD, which is 149.09. Actually, I can round up. 109.1 degrees. Okay. Once I get this angle, and I know that I have 360 minus x and x, now I can use Theorem 1013 to find the inside arc. Now that everything is established. So for step number 4, I can say that 149.1 is equal to 1/2 of the outside arc, which is 360 minus x, minus the inside arc, which is x. All right, so that turns into 149.1 equals 1/2 of 360 minus 2x. So I can multiply by 2 on both sides, subtract 360 and divide by 2, and that would give me my x. So x is going to equal 30.90 degrees. And the book says about 31. So, yay, 30.9. That is my inside arc. So if I wanted to find my outside arc, I would just subtract 360 minus that, and that would give me my outside arc. Okay. Step 1, establish your inside and outside arcs in terms of x. Step 2, recognize that you have a right triangle here, and you can do trig functions. So we did inverse sine to find the angle. Step 3, we multiply that angle times 2 to get the whole entire angle. And in step 3, we used equation 1013 to solve for the arc that we were looking for. Okay. Knowing how to do that, we can now set up 6. 6 is the same exact problem. The only difference is we're looking for a different arc. Arc is on the outside, not on the inside. But the situation is exactly the same. So in this case, we have our circle. We have our line that's tangent to both. So this only works when it is two tangent lines. This is Q. This is T. This is R. We're at the center here at S. This is the center of my circle. So we have it going that way and that way. They're going to be perpendicular to both of those guys. And if it's perpendicular, then that means that this line here is a perpendicular bisector. So this is perpendicular, this is perpendicular, which means that this angle and this angle are the same. They said this outside is 2. They said this is 2, then this whole entire thing is 5. All right, so this is 5. Okay, so that's 5, that's 3. We're looking for angle, well actually, no, let me set the parameters first. So we're going to call this outside guy here. And I guess there's some U up here too. Here's a U. We're going to call this outside arc X. And then we'll call the inside arc Y. So, like before, step number 1, X plus Y equals 360. So we know that Y equals 360 minus X. So this guy here should be blue. Is 360 minus X. So X, 360 minus X. All right, so we have this right triangle right here. Q, TS. We're looking for angle Q, TQR. So step 2, we're going to do inverse sine because it's opposite over hypotenuse of 3 over 5, and that's equal to angle TQS. And that equals .86 .87 degrees. Step 3, we're going to multiply this by 2 to get the whole angle TQR. So 2 times 36.87 gives me the measure of angle TQR. And that equals 73.74 degrees. So once I got those two, and once I got that angle, then I have enough to find what X is, the outside arc. And I can do that by using equation 1013. So the measure of angle TQR is equal 1/2 the measure of the outside arc, which is TUR, minus the measure of the inside angle, which is TR. All right, so TQR we just said was 73.74 degrees. 1/2. All right, so TQR, that's my outside angle, that's X. TUR, and that's going to be minus 360 minus X. Okay, 360 minus X. So then that's going to be 73.74 equals 1/2 of, I'm going to move this over, so this is going to be distributed, right? So that's plus X, so this is going to be 2X minus 360. Okay. Multiply by 2, add 360 on both sides, divide by 2, or if you want to distribute this 1/2 out, we can say that this is X minus 180. Actually, I'll rewrite it down here. I don't want to confuse people. So 73.74 equals X minus 180. So all I have to do is just add 180 to both sides. And I get that the outside arc, measure of TUR, is equal to 253.74 degrees. Which makes sense, bigger than 180. Okay. So, same thing as we did in the example problem. You establish your arcs in terms of X. You recognize that you have a right triangle here, so you can use trigonometry. Inverse sine of 3/5 gives me this angle, 36.87, but that's only half of the angle because it's a bisected angle. So I multiply it by 2, and then I have enough information. I have the angle, and I have these arcs defined as terms of X. Substitute them in, solve for X, which is the same thing as your angle. All right, guys. This is it. You may have a great rest of your day.